All right, so what we're trying to do here is we're trying to solve this final question, basically talking about a carnival ride. And we're going to have to think of this in kind of two ways. One, in the geometrical scenario, because we've got a centripetal force and we need a radius. So we're going to need to base off this 12 meters. What is the radius of the actual path this object is following? And secondary to that, we also need to look at this in terms of the forces. So we've got a tension in this cable. And that tension is separated into two force components. We've got a Ty and a Tx. We know the vertical forces, right, cancel each other out. So we have a weight pointing down, and then the y component of this tension points up. But it's got to be equal and opposite to weight. Okay, and then the other part of that tension, this Tx, or this horizontal component of the tension, well, that's what's providing the centripetal force. Okay, so that's kind of where we're at. So Ty would be found then as the overall tension, okay, times the cosine of 65, and that's equal and opposite in magnitude to weight. So we could then say mg, what's going on here? Mg is equal to T, right, that's the overall tension, times the cos of 65 degrees. That's our vertical scenario. Okay, so next up we got to deal with the horizontal, and this Tx actually, what it really is it's our centripetal force, right? So it's going to be equal to mv squared over r. Yeah, okay, perfect. Or actually we could also consider it as m4 pi squared r all over t squared. We'll see which makes more sense. I believe in this case we're looking for velocity, so we wouldn't end up using that. However, it's possible that you get a question similar to this where you do want to find the period, let's say, and you would go from there.
Both of these we have two exponents that we don't know.
Right, so what we'll do is we'll try to like mingle them together. But I just want to point out, and someone pointed this out, this T in this formula is not tension, that's period. It's maybe a little unfortunate that I used a T here. Maybe I should just call that FT, and it'll be maybe a little more, you know, safe. We're not going to confuse those two things. Okay, now the radius here. Okay, we don't actually have that radius given to us, do we? However, we should be able, if we know that this is a 12-meter cable, let's just redraw that. Okay. Then, 12 meters, okay, and a 65-degree angle, okay. Well, that radius then should just be equal to 12, right, times the sine of 65 degrees. So, okay, so let's think about the horizontal scenario here, right? So Ft of x, so that's the force of tension in the x. You could think of that as equal to Ft, and sorry, I should leave this as Ft as well, as Ft times the sine of 65 degrees. Okay. And since we've kind of established that that is also, right, that x component of the tension force is providing the centripetal force, then it should be equal, right, to mv squared over r. However, we've established that r is 12 sine 65. So we should get this. So we don't have what Ft is, we don't know, and we don't know what the velocity is. Okay. However, we did establish this vertical scenario up here, so maybe we can use that in some way. So we also know that mg should be equal to Ft times the cosine of 65 degrees. And I see this Ft here would be nice if we could get rid of it and replace it with something we do know, okay? So let's do a little rearranging and see what we could do. So ft then should be equal to mg divided by the cosine of 65 degrees. Okay, which makes sense, right? To get ft, if we knew what mg was and divided by the cosine, we would get, right, out whatever the tension value is in here. But what the usefulness of this is we should actually be able to slot in mg over cos 65 into this formula. And then we've eliminated, okay, one of the unknowns, and we're left with only one unknown, which is our velocity, all right? So we have to be a little bit tricky to solve a question like this, but I think we've done enough work now that we can actually solve it, I think. Okay, so mg, right, over the cos of 65 is going to replace ft, and we're going to multiply that by the sine of 65 degrees. And that should translate to be equal to mv squared over 12 sine of 65 degrees. And by the way, if you were trying to do this in terms of like finding a general formula for this, you can just, you know, substitute in a value, let's say L for the 12. We're specific to this scenario because that's 12 meters. But if we want to be just generic, we could actually just leave an L in there. And maybe if you're okay with it, that's how we'll finish this up. I'll just swap out an L for that, just to make a kind of like make a universal formula. If you were to ever run across a problem like this again, I don't know, say like you end up with a job designing Carnival rides or something. It's probably pretty legit future career for some of you. Okay, so this 12 is particular to this problem, but you could imagine the same problem with different angles, possibly. You could also replace all the 65 degrees with just the value theta to mean the angle. So I've just gone ahead and dumped the 65 because, again, it could be any angle, and put in thetas there, okay? Now, someone has pointed out that there's a trig identity that you know, which is sine theta over cos theta should be equal to tan theta. I guess where that comes from, right, would be just thinking of how a right triangle shakes out. You know, if this is part of the unit circle and this value is 1, right, and you've got theta, you got theta here. Okay, well, over here is 1 cos theta, which is just cos theta, right? And over here is 1 sine theta. Okay, and then tan theta is just opposite over adjacent. Well, opposite is sine theta, and adjacent is cos theta. Okay, they're multiplied by 1, but we'll just dump the 1 because 1 times anything is just itself, and so tan theta is indeed sine theta over cos theta. If you ever forget that, just draw a triangle and think about it a little bit, okay? So mg tan of theta equals mv squared over L sine of theta. And I suddenly see here that the mass in this scenario actually ends up being a cancelable thing. So we can get rid of that. And essentially what it means is the velocity will, the velocity and the length will dictate the angle that you're dealing with. Okay, velocity and length dictate the angle. The actual mass at the end of the rope should not matter. Okay, so if you're going at a certain velocity, you should have a certain angle regardless of the mass that you put there. Okay, so now all we need to do is just solve for v squared. So let's see here. That should be this, I think. V should be equal to g tan theta over L sine theta. Oh, no. Sorry. Nope. That's not how the algebra works. We're going to multiply that off. Sorry. So it should be g tan theta multiplied by L sine theta. And that's, of course, equal to v squared. Does tan theta times sine theta give us anything useful that we know of? No, there's no trig identity like that. Okay, it doesn't really matter because it's solvable now anyway because we have the angle. I was just wondering if there's a shorter way to do it. But we could say GL. Okay, I think that's where we get. Yeah, I think so. So if you do get that, that's what I got by actually putting in the number 220 and approaching this in a slightly different way. So we could call this 10. Why not? Just to be lazy. L was 12. Then sine 65 times tan 65. I believe you should get around 15. So you should get somewhere around 15.3 meters per second. And that does match up with, what's that? Yeah. Oh, yeah. It would depend whether you use 9.8. Like, I think 9.8 gives you 15.1 and 10 gives you 15.3. But roughly, I mean, I guess if we round for sig figs, probably would be something like 15 meters per second. Okay. But anyway, the point is, right, you can find a way to solve these problems really without any new knowledge beyond some geometry understanding and this idea that we've had before of vector components. And although it's maybe an kind of like unfamiliar at first, there's definitely familiar elements to solving a problem like this. All right. So yeah, we'll kind of leave that one there.